The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Alrighty, so today we're going to start the final chapter, chapter 11. We're going to look at sections 11.3 and 11.4. And so let's go ahead and get started. So we've considered functions, equations, linear, y equals mx plus b. So like maybe y equals, let's say, 2x or 2x plus 4. Linear equations, the graph of which is a straight line of some sort. We've considered second degree or quadratic equations in the form y equals ax squared plus bx plus c, or something like y equals x squared, which is a parabola. Today we're going to look at a new kind of function called an exponential function. They will be in the form of y equals b to the x power, where the exponent is the variable. Okay, so like y equals 2 to the x. So instead of 2x, which is linear, x squared, which is quadratic, 2 raised to the x power, which is an exponential equation. Okay, I'm going to switch screens here, so hold on and hopefully everything will work just fine. And let's see here. We want this one. Okay, so let me switch here. So now can everybody see the graphing screen? Somebody just say if you can.
Yes.
Thank you. All right. So let's take a look at a basic exponential equation. So let's look at y equals 2 raised to the x power. Now recall that I said whenever I start a new graph of some equation or function that I'm not familiar with, so to speak, I'm going to make a table and I'm going to take the x values and go from -3 to +3. So let's see what happens when we do that. So if x is -3, y equals 2 to the -3 power. Recall that you can rewrite a base raised to a negative exponent as 1 over that base raised to a positive exponent. So this becomes 1 over 8, or 1/8. Any questions about that? All right. If x is -2, y equals 2 to the -2 power, which is 1 over 2 squared, or 1/4. If x is -1, y equals 2 to the -1 power, which is 1 over 2 to the 1 power, or 1/2. If x is 0, y equals 2 to the 0 power. Recall that any base other than 0 raised to the 0 power equals 1. If x is 1, y equals 2 to the 1 power, which is just 2. If x is 2, y equals 2 squared, which is 4. And finally, if x is 3, y equals 2 to the 3rd power, which is 8. Okay, let's see here. We don't have that symmetry like we do with a parabola, but notice these are reciprocals, these are reciprocals, these are reciprocals, the y values. All right, let's graph this thing. If x is -3, y is 1/8, so that's going to be about there. When x is -2, we're going to go up to about 1/4. When x is -1, we're up to 1/2. When x is 0, we're at 1. When x is 1, we're at 2. When x is 2, we're at 4. When x is 3, we're all the way up to 8. All right, let's see if we graph this thing. And that's going to continue on in that direction. That's going to continue on. And so there we get the graph of y equals 2 to the x power. Notice, if I continued on 4, 5, 6, this thing is just going to get larger and larger, isn't it? What about going the other direction? -4, -5, it's going to be 1/16, 1/32. So going to the left, this thing is going to get closer and closer to the x-axis, but it will never reach it. Going to the right, it's going to just get larger and larger and larger. So let's see, what are the characteristics of this thing? Well, the domain would be what? All real numbers. It's supposed to be negative and positive infinity. The range would be what? Not 0, but greater than 0 up to infinity. What about the x-intercepts? There are none, are they? Are there? Because it doesn't cross the x-axis. The y-intercept would be at 0, 1. And we also say that this thing is increasing over its entire domain. Okay, so the domain is all real numbers. The range is greater than 0. There are no x-intercepts. The y-intercept is at 0, 1. It's increasing over its entire domain. All right, any questions here before we go on and look at another example? Okay. Let's take this y equals 2 to the x power. And let's start with it again. -3 was 1/8. -2 is 1/4. -1 is 1/2. 0, 1, 1, 2, 2, 4, and 3, 8. Okay. And again, we'll graph it here. All right. Let's see. I think I got that pretty close. We'll just fudge a little bit there, but you get the general idea. What's happening as x increases? Each time x goes up by 1, what is y doing? It's doubling. Okay, do you see that? 2 times an eighth is a fourth, 2 times a fourth is a half, 2 times a half is 1, etc., etc. Okay, let's take a look at this one. Get this mouse here. Where are you? Ah, there you are. Okay, I'm going to change it to red. And let's take a look at y equals 3 to the x power. And we're going to put in those same x values. Now, when the base is 3 instead of 2, when x is -3, y equals 3 to the -3 power, which is 1 over 3 cubed, which is 1/27th. When x is -2, y equals 3 to the -2 power, which is 1 over 3 squared, which is 1/9. When x is -1, y equals 3 to the -1 power, which is 1 over 3 to the 1, which is 1/3. When x is 0, y equals 3 to the 0, which is 1. When x is 1, y equals 3 to the 1, x is 2, y equals 3 squared, and finally, y equals 3 cubed. So what's going on here? Instead of them doubling, they're tripling, aren't they? Well, over here, we're below, but then we've got this, and this, and this, and so what about the characteristics? Well, the domain is still all real numbers. The range is still greater than 0. There are no x-intercepts. The y-intercept is at 0, 1, and it's increasing over its entire domain. So basically, all of these characteristics still work. But notice, because it's tripling, it grows more rapidly. What if we were to consider y equals 5 to the x power? It would have all the same characteristics, except that it would grow even faster. So, you know, it would still have a, what? All real numbers are the domain, the range is greater than 0. It has no x-intercepts, the y-intercept would be at 0, 1, but now it's going to grow even faster. Okay? Any questions about that idea? All right, now, let's take a look at, let's do this. Let's delete this. And let's look at, let's see, we still got green. We use green. Let's look at y equals 1/2 to the x power. And let's see what that does. Okay. I draw such lovely straight lines here. Not. Okay. -3, -2, -1, 0, 1, 2, and 3. Now, be careful. So y equals 1/2 to the x power. If x is -3, we get y equals 1/2 to the -3 power, which is 2/1 to the +3 power, right? The reciprocal of the base, and then you change the sign of the exponent, which is 2 cubed, which is 8. Okay. If x is -2, y equals 1/2 to the -2 power, which is 2/1 to the 2 power, which is 2 squared, which is 4. If x is -1, y equals 1/2, excuse me, to the -1 power, which is 2/1 to the +2 power, 2 to the 1 power, or just 2. If x is 0, y equals 1/2 to the 0 power, which is 1. If x is 1, y equals 1/2 to the 1 power, which is 1/2. If x is 2, y equals 1/2 squared, which is what? 1/4. And finally, cubed, 1/8. So what's happening here? Instead of them doubling like they were in this example, they are halving, so to speak. Since the base is 1/2, each time we increase x by 1, the y value gets cut in half. So what does that thing look like? Well, let's see. It's going to start over here and then go to here and here and here and here. And it's going to look like this. The domain is still all real numbers. The range is still greater than 0. There's still no x-intercepts. The y-intercept is at 0, 1, but we say this thing is decreasing over its entire domain. Okay. So here's what we get. If the base is greater than 1, this thing increases. If it's less than 1, it decreases. Well, what about if it is 1? What does that look like? Well, let's just take a look at y equals 1 to the x power. Let's see what that's going to do for us. -3, -2, -1, 0, 1, 2, and 3. Well, y equals 1 to the -3 power would be 1/1 to the 3rd power, which would be 1/1, which is 1. If x is -2, y equals 1 to the -2 power, which is 1/1 squared, which is 1/1, which is 1. If x is -1, y equals 1 to the -1, which is 1/1 to the 1, which is 1/1, which is 1. Can you see what's going to happen there? Okay. That's not going to fit the properties and things that are going on with those other functions. That's basically just going to be a straight line. So basically, we have this situation. We say that if b is greater than 1, we get an exponential graph that's increasing over its entire domain. If b is less than 1 and greater than 0, we get this situation. B can't equal 1 because when it does, it doesn't fit the pattern. Okay, and also b can't be negative. So let's just say b has to be greater than 0. Okay, So the base has to be greater than 0, but it can't equal 1. If it's between 0 and 1, it decreases. If it's greater than 1, it increases. Okay? I could go through and show you examples why it doesn't work when it's negative, but I'm not going to do that this morning. Okay. So now take a look at some situations. Let's go back to just plain old y equals 2 to the x power. Okay. -3, -2, -1, 0, 1, 2, 3, 1/8, 1/4, 1/2, 1, 2, 4, and 8. And again over here, get this picture. All right, now let's look at y equals 2 to the x, and then let's add a constant out at the far end. How about +3? Okay. So wouldn't this be the same thing as that? So we get these values, but then adding 3 to the y value, this is going to be what? 3 1/8, 3 1/4, 3 1/2, 3 + 1 is 4, 3 + 2 is 5, 3 + 4 is 7, 3 + 8 is 11. Okay. What's that going to do to the graph? Think back to the parabolas. Y equals x squared. Y equals x squared plus 3 went up 3 units. So y equals 2 to the x plus 3, everything's going to move up 3 units. So we're going to go up here 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3. Let's see here. 1, 2, 3, 1, 2, 3. And we're going to get this picture. Okay. So now the domain's all real numbers. The range is greater than 3. There's no x-intercepts. The y-intercept is at 0, 4 because everything's moved up 3 units. Okay. What if we had this? Let's say y equals 2 to the x minus 5. What would that do? That would move everything down 5 units. 1, 2, 3, 4, 5. Let's see here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. And it's going to look like that. Domain all real numbers range is what? Greater than -5. The y-intercept is now at -4. Oh, now there is an x-intercept, isn't there? Yeah. Okay. So just like with parabolas, by adding a constant term out beyond the exponential term, we can move this thing up or down vertically. What about moving it side to side? Well, okay. Let's see here. Let's do this, and we'll get rid of all that. And go back here. Let's say we have y equals 2 to the x plus 2. So now that plus 2 is not a separate constant term. In fact, we'll put parentheses around it to show that it's part of the exponent. Okay. So that's on the inside. What do you think it's going to do? It's going to move it 2 units to the left. So this is going to be here, 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 there. It's going to look like this. Okay. So that's going to go to the left 2 units. What if I had y equals 2 to the x minus 3? That would move it that way 3 units. Okay. Now, I can't graph this, but I can graph that, because there the base is the 2 and the negative is an afterthought. Well, how is that going to compare to that? You're going to take all of those values and negate them. So instead of it opening up like this, it's going to look like that. Whoops, you can't see that maybe. I don't know. Can you see that? Let me put it over here. Instead of going up like that, it's going to go down like that. Okay, so it's going to look like this. All right. Having said all of that, I want to get into some more information than just the graphs. How are we doing? Okay, so let's see. We're going to switch back to our other screen. And let's see here. Stop share. All right, can you see my whiteboard? Somebody?
Yes.
Okay, great. Thanks, sir. Okay. Let's say we have the following situation. Okay. We have P of T equals 6 million times 2.3 to the T power. Okay. Now, this is an exponential function. The exponential part would be this, but then there's this multiplier in front, okay? T stands for time in hours. It says a colony of 6 million bacteria was determined to be growing in the culture medium shown in an illustration, and there's some drawings of a petri dish, but you don't need to see those. If the population P of bacteria after T hours is given by this function, find the population in the culture later in the day using the information illustrated. And basically it's 4 hours later, okay? But before we do that, let's take a look at this function again. At the beginning of time, at the beginning of this problem, when time is 0, in other words, what is P of 0? 2.3 to the 0 power equals what? 1. 6 million times 1 is 6 million. So even though they told us in the problem that there was 6 million bacteria to start with, we could determine that just looking at this function. All right. Now, are these bacteria growing or decaying? Well, if we look at the base of the exponential part, we see that the base is greater than 1. Remember, if the base is between 0 and 1, it's going to decrease. If it's greater than 1, it's going to increase. So what we have is a population of 6 million bacteria, and the population is growing. Okay, we can determine all of that just by looking at the original function. Now, they want to know the population 4 hours later, and T is measured in hours. So basically, they want to know what P of 4 is. So we'd have that. So in our calculator, we're going to go, let's see here, 6 million times 2.4 to the 4th power, and I get 199065600. So 167, hang on here. What did I do wrong? 4. Oh, I put in 2.4. I see that right here. I went from 2.3 to 2.4. And I erased it because I scribbled it. All right, so let's try that again. Nobody else is awake, apparently. All right, so 6 million times 2.3 to the 4th power 167,904,600. So it grows to 167,904,600. Wow. So from 6 million to 167 million in just 4 hours. That's what you call exponential growth. You'll hear that expression, exponential growth, when on the news or something, in science, they'll be talking about exponential growth or decay of a population. That's what's going on here. All right. Any questions about this? Okay. Let me ask you this. Here is a function representing a population. Okay. It says the population of North Rivers has this function where t is measured in years from the present date. At the present date, what is the population of North Rivers? Okay, can anybody tell me? Well, since when t is 0, this becomes 1, and 1 times 3745 is 3745. That's the starting population at the beginning of this problem. Okay, now, is the population growing or decaying? The base is between 0 and 1, so it's decaying or decreasing. By what percent is it decreasing? 7%. Where did I get that? Well, 0.93 is 93%. As time goes on, each time t increases by 1, we're going to multiply this by 0.93. So we're going to be taking 93% of what's there, which means we're going to be losing 7%. And let's see, time in this case, it's measured in years, so it's losing its population at a rate of 7% per year. Okay, now I'm going to look at a formula, compound interest formula. Okay, and this is what it looks like. A equals P times the quantity 1 plus R divided by K, the whole thing raised to the KT power. Okay. P is the principal, the initial amount invested. Okay. A is the final amount. I'm going to say accumulated amount. R is the annual interest rate. K is the number of compoundings per year, and T is time in years. Now, what do I mean by the number of times it's compounded? Okay, so compound interest, let's say you invest $100 at 5% compounded semi-annually, twice a year. That means at the end of 6 months, they calculate the interest that's been accumulated. They leave that in the account, and then the next 6 months, you're not only getting interest on the original principal, but now you're getting interest on the interest that you made the first 6 months. And so the more frequently it's compounded, whether it's annually, once a year, semi-annually, twice a year, quarterly, 4 times a year, monthly, 12 times a year, daily, 365 times a year, the more frequently it's compounded, the more interest you're going to gain at the end. Okay, now let's take a look at a problem using this formula. So A equals P times 1 plus R divided by K to the KT power. All right. It says compound interest, an initial deposit of $10,000, so P is $10,000, earns 8% interest. So R is 8%, which we're going to convert into a decimal number. Careful you don't mess that up. Compounded quarterly, so 4 times per year. How much will be in the account after 10 years? So A, the accumulated amount after 10 years. All right. So A equals $10,000 times 1 plus 0.08 divided by 4, all raised to the 4 times 10 power. Now, let's write this a little nicer. 4 times 10 power. I can do this 2 different ways. I can simplify 4 times 10 and make it 40. I can simplify 0.08 divided by 4 and make it 0.02. And then I can take 1 plus 0.02 and write it as 1.02. I can do all that ahead of time. Okay. In fact, let's write that, what I just said. So let's see here. So in other words, I could simplify that and simplify that and then simplify that and punch that into the calculator. And that's fine. However, let's say that this number doesn't divide nicely, okay, for whatever reason. Don't divide it and then round it off. If that's the case where it doesn't come out exact nicely, leave it as it is in the beginning and just put that whole thing into the calculator, okay? So in fact, I'm going to do it that way. So on the calculator, to do the whole original thing, I'm going to put in 10,000, okay? So 10,000, left-hand parentheses, 1 plus 0.08 divided by 4, close parentheses, power key, and then parentheses, 4 times 10. Okay, equals. And I get, so this is money, so I get $22,080, and it actually is 396. But since we're talking money, I'm going to round to the nearest cent. So it's going to be $22,080.40. Okay. Unless it says otherwise, always round money to the nearest penny because you're not going to be handing out a fraction of a cent. Any questions on this example? Okay, let's take a look at this situation. It says comparing interest rates. How much more interest could $1,000 earn in 5 years, compounded quarterly, if the annual interest rate were 5.5% instead of 5%? Okay, so what we're going to do is we're going to have 2 different scenarios. In both cases, the principal is going to be $1,000. In both cases, let's see, time is going to be 5 years. Each one is compounded quarterly. Let's see here. But the first one, the interest rate is going to be 5%. And the second one, the interest rate is going to be 5.5%, which is 5.5%, which is 0.055. Okay? So everything else is going to be the same, except we're going to increase the interest rate by 0.5% per year, and then find out how much, let's see here, how much more interest will be gained at 5.5%. All right, so here we've got A equals $1,000 times 1 plus 0.05 divided by 4, all raised to the, 4 times 5 power. And over here, A is going to be $1,000, 1 plus 0.05, 5 over 4 raised to the 4 times 5 power. And, 4 times 5 is exactly 20. That's nice. Probably I would have just written 20 instead of 4 times 5. But the 0.05 divided by 4, or the 0.055 divided by 4, may or may not come out nicely. It does, but it gets kind of long. So I'm just going to punch it in like it is, okay? So the first one, 1,000, parentheses, 1 plus 0.05 divided by 4. Close that up, use the power key, parentheses, 4 times 5, close that up. I get 1282037. Goes on further than that, but that's going to round up to that much. Okay? Now, let's do the second problem. 1,000, parentheses, 1 plus 0.055 divided by 4. Close that up with a right-hand parentheses. Power key raised to the 4 times 5 power. And I get 1314.0665. This is going to round up, so 1314.07. So now I'm going to take 1314.07 minus 1282.04, and the difference is $32.03. So that may not seem like a lot, but investing $1,000 over a 5-year period, if you have a 0.5% higher interest rate in this scenario, you get $32.03 more. Okay. So if you're collecting money, the higher the interest rate, the better it is for you. Okay. All right, let's take a look at another example, kind of an extreme one. This says if $1 had been invested on July 4th, 1776. So we're going to invest $1 at 5% interest. So this is PR, 5% interest. Compounded annually. What would be its worth on July 4th, 2076? So we went from 1776 to 2076. The time would be 300 years, right? 1776 to 76, okay? So 300 years, all right? So what would it be worth? $1 invested at 5% compounded annually for 300 years. And 300 times 1, okay? So basically, that's what's 0.05 divided by 1? That's just 0.05. And 1 plus that is going to be this. So this one simplifies easily. So 1, oops, turn the calculator on first. 1 times 1.05 raised to the 300th power. Wow. And I get this, 227,399.6.129. So that would be, what, $2,273,996.13. Don't you wish you had made that investment? Well, of course you weren't around then, neither was I. But anyway, there's your general idea. So let's do a recap of what we've looked at so far in this section. We're talking about exponential functions of this form, where the domain is all real numbers, the range is greater than 0, the base has to be positive, but it can't be equal to 1. So the base has to be greater than 0, but not equal to 1. If the base is greater than 1, it increases. If the base is between 0 and 1, it decreases. And then we've got this compound interest formula where P is the initial amount, R is the annual interest rate, K is the number of compoundings per year, T is the time in years, and A is the final amount. All right, we are now going to stop the recording.